but they need some improvement over there. So first, if I ask you to draw the circuit diagrams for inverting amplifier, non-inverting amplifier, and the differential amplifier, can you do that? Okay, see? So I'm going to draw it here really quick so you can look at it during the lecture. So eventually we'll do an in-class exercise on it. Okay, so see, inverting, you need a resistor. Why? Because it's converting voltage to current. That's a feedback resistor. I've done this thousands of times. That's why I can draw it easily. But you guys just need more practice. Grounded. Power rails. That's inverting configuration. Why? Because the input goes to the inverting terminal. And you need a negative feedback. Non-inverting, still keep the minus on the top. Keep in mind, doesn't matter inverting or non-inverting. What kind of feedback do you need? Negative feedback. Always negative feedback, which means the feedback is always going to the negative input. I have a better Sharpie. Oh, no. However, you ground here. And you put your signal here. That's why it's non-inverting, because it's input. Input goes to the non-inverting terminal. Sometimes you see people draw this one on the top. So plus on the top, negative at the bottom. It's still the same circuit. Just compare the differences between these two. Inverting or non-inverting depending on which the input signal is connected to. It's connected to the inverting and the inverting configuration. Connected to non-inverting is a non-inverting configuration. You have two rails.
What are the, I know that the rails are saying pounds, but basically what are they doing?
These two?
Yeah.
Yeah, power and ground.
Oh, just power and ground.
Yeah. So for if you ground here, right, you need negative. It's called dual power supply, which means you don't ground the bottom rail. You give a minus voltage here, give a plus. Let's just give number like 15 volts and minus 15 volts. It's a really common voltage being used in the lab. Okay. These two. If I'm asking you to draw a summing amplifier, have heard about that? Summing amplifier. We can sum it here. We can sum it here. We can sum it here. But now let's just sum it at the inverting terminal. How that works? R1, R2, R3. You got V1, V2, V3. Inverting terminal, summing amplifier. How to find out the VO or the voltage gain over here? How that is calculated? No difference. 0 volts, KCL. Right? So the three currents flowing in, and none of the currents is going into the op-amps. It's all flowing here. How to list the KCL here? V1 minus 0 over R1 plus V2 minus 0 over R2 plus V3 minus 0 over R3. That's the three current streams flowing into it, and nothing is going into the op-amps. It's all flowing merged and flowing into the RF through RF. So that equals 0 minus V out over RF. That's it. So op-amps problems from the scope of the exams in this class is really simple. Circuit 1 level, beginner level, super simple.
So is this, even though there's like three voltage sources, is this only create like one sine wave, or there be three sine waves?
Depending on the signal, but it just follows this equation. Doesn't matter it's a sine wave or DC voltage, doesn't matter. It just follows this equation. Doesn't matter what kind of waves they are. Is that clear? 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 Clear. Okay? So one of them will be on the in-class exercise later, okay? So I do have time to waste to cover something else. What's that?
It doesn't change any of them if it has like a connection for the amplifier, the triangle. A few of our exam problems in the homework, those had a connection between the two of them.
Connection between what?
Like the negative and positive terminals, the wires connected before them.
I don't wire connect before them. I don't think these will be connected. It's just either input going to here or going to here.
I mean, just in like homework examples, it did that before.
Okay.
Does that change which type it is or no?
Do you know what kind of circuit? How can I change it here to make that circuit happen? What to change?
I don't know. I'll try to find one.
Okay, then email me. Okay. All right. Another one, yeah, before I move forward with something else. Difference amplifier, which is it's a high performance version. So when I teach circuit 1 at a different institution, I'm going through all the derivations for this version, and also another one called instrumentation amplifier. I spent a whole week. But in here, we don't have time to go through the derivations. So the only thing we can do is just give you the equation, you know the gain, you know the structure, that's it. So the structure looks like this. And what the thing you need to know is this is a super practical configuration, and it's being used in the industry a lot. It looks slightly different, right? Since you have two resistors and R2, R1, they have the same values. It's symmetrical, so I'm labeling these as the same resistor. So keep the same ratio will be able to improve the quality of the amplification. It's rejecting noise. Why it's rejecting noise? It's going through whole the derivation. I don't have time to run it. Not difficult, but just let you know. You have to make it symmetrical in order to improve the performance. Okay, so we got a V in, V1, V2, and V out. That's called a difference amplifier. Sometimes you can see it's a differential amplifier. It's the same thing. They can be used interchangeably. Or differential amplifier, doesn't matter. It's just amplifying differences. So the gain is from the minus. Oh, that's right. Yeah. So the plus minus the minus input and times R2 over R1. That's the gain. Again, you can put on the cheat sheet, but I'm not going through the derivation here. It's called a differential amplifier. Can you tell the difference? What's the difference? Here and here, what's the difference? You can visually tell. Yeah. Yeah, voltage source on both sides. Okay. Yeah, and you're saying there's a voltage here as well. Yes, it's zero, right? It's zero. But anyway, so they are just different. You can just look at the resistor. So you can see here is the two feedback resistor, and this one has no resistor on the non-inverting terminal and just shorted the ground. But this one has two resistors. So and two inputs. That's a differential amplifier. It's a high quality amplifier. It's rejecting noise, only amplifying signal. Why? We don't have time to run through it. This, just normal inverting, beginner, first level, inverting amplifier. It's gonna have a phase shift because it's inverted. This one is not inverting the signal. Directly high impedance input because voltage is getting into here, no current, the voltage being measured to here, and then you do the calculations. Oh, what's the gain of this guy? Something else you can put on the cheat sheet. VL over VI, V in. Let's just say VI. For the inverting, it's minus RF over R1. Okay? For non-inverting, it's VO over VI equals 1 plus RF over R1. But 1 plus the ratio. For this guy, it's this. Okay? Need to know that they are different, very different. Okay, let's come back because on Wednesday we have homework 9 due. So something we have to cover today. Let's do a review on that first. I'm not going through all the details, nitty-gritties here again, but let me just draw this down. This equals this. Conceptually have tell me where this comes from. No. Difficult, yeah. Could be. Euler's equation. That's the beginning point. Why? Because it's a given, right? So you start from here. You start from here. Okay? There's no time. It's a frequency domain. It only shows the amplitude and angle. These are angles. Where's the amplitude? I didn't write amplitude here. So we can, if you want to include amplitude, it's this. So sometimes you'll see a complex number because A times cosine theta, so this becomes A cosine theta plus A j sine theta. This starts getting confusing. Go back to the lecture last time. That was Friday, I guess. Okay, I explained more, but I don't have time to do that again today. So if this can represent any type of signal, anything, any signal, and this is a complex. It's called rectangular form. Why it's called rectangular form? Because on the complex plane, you have J here and real here. So actually I. Imaginary and real. Okay? So A cosine theta will be here. For example, this is the amplitude. The length of the bar is A. A cosine theta is this guy. Sine theta will be this guy. So this bar represents amplitude and the angle. So if I'm asking you, what is a phasor? Phasor. We talked about that on Friday. We only care about amplitude and angle. There's no time. That's why it's called steady state. You'll see this a lot. Because, you know, the definition of this one, you'll see, we don't have to study. Trying to dig in very deep into it. Whenever you see steady state, you just assume that all the signals have the same frequency. That's it. So we don't have to worry about the time. So we can feel free to use the phasors. So whenever you see steady state, in the steady state, whatever, blah, 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 okay? Don't worry about that too much. What is steady state? No worries. So that just telling you that you can use the phasors, do all the math. It's making things easier. So don't worry about the time because they have the same time. Eventually you can convert it back with the time. But now let's just worry about the phase or the angle and the amplitude. I know it's confusing, but revisit the Friday's lecture I recorded. So now let's come back here. Assuming that this guy can represent any signal. Why? I don't have a phase shift, but you know, this guy is basically a phasor. This is the phasor because it has amplitude and angle information here. Because I can, based on this guy, I can draw a bar here. That's it. So if people ask you, what is a phasor, really? It's just a rotating bar. Just a rotating bar. The bar's length is amplitude, and the angle in the unit circle plane is the phase. That's it. Phasor is a rotating bar. Okay? That's the phasor form, and that's a rectangular form. Why I can do that? Euler's equation. That's it. Is that clear? Why is the rectangular form? It's a rectangular. It's a rectangle. Okay? If I'm not giving you this, I just give you a, arbitrary complex number. For example, 5 plus 3j. You'll see this a lot. What kind of form? Rectangular form, but this is called a polar form. Sorry, I didn't talk about this. It's a polar form. It's a rectangular form. If this is given, you know this is what? Rectangular form. Can you convert it to this? Yes. Super important process here. How do we convert it? Back and forth. Here to here, easy, right? Keep A in the front of it, it's amplitude. And just directly write down cosine theta, and sine theta here. So if this is given, can you find out cosine theta and sine theta? Yes, use a calculator. So from polar form to rectangular form, very simple, calculators. And then you do the calculation, A times this guy, A times this guy, eventually you get a rectangular form like this, for example. All right? However, if this is given, can you convert it back? How? What's the bar's length? It's gonna be like 5 square plus 3 square and square root, right? Five, 3. What's the length of the bar? Which is the amplitude. Amplitude of the sound wave. Yes. So why is the amplitude of the sound wave? I'm repeating myself. Okay, why is the amplitude? So the bar starts from here, okay? Starts rotating from there. If this is time domain, when it starts rotating here, and you're projecting this one to here, so at the very beginning, the cosine wave shows this. And eventually, when it's rotating, it comes to here, so you are projecting this here, so that's why the amplitude comes to here, right? So that's how this rotating bar forms the sine wave. You stretch it in the time domain, so you are forming a cosine wave. If you shift the cosine wave, you're getting a sine wave. That's why that doesn't matter if it's cosine, sine, phase shift, it doesn't matter. They are both called sinusoidal waves. If I'm telling you, hey, this is a sine wave, is this correct? This is the sine wave. Yes. It is the sine wave. Is it the cosine wave? Yes, it doesn't matter, just with the phase shift. It's just a rotating bar with the angle, depending on the starting point. If you, with the angle here, you start from here. So ignore this, right? You start from here. Then it's gonna do this periodic oscillations. It's just a starting point. Doesn't matter, it's a phase. It's a starting phase. It could be the beginning if you start a bar from here. Because at the very beginning, your amplitude is what? The peak voltage, the peak. Whatever the amplitude can reach, the maximum. Okay, because that's the maximum. Whenever it rotates that direction, the amplitude getting smaller. That's the maximum you can get. So is this a sine wave? Yes. It's carrying information. What kind of information? You did raise your hand. Anyway, so what's the information this one carries as a sine wave? Two information. What are they? Time? Time? No time. Phasor, no time. What are they? Amplitude and phase. What's the amplitude? What's the amplitude? 1. So what's the length here? 1. Can I change the amplitude? Yes. That's A. Doesn't matter. What's the angle? Phase. Starting point is theta, right? So is this a sine wave? Yes, it carries information. What are they? Amplitude and phase. No time. Okay? So assuming the time is given.
If we are combining phasors, do we just set like the time equal to?
They are all the same, yes. For the steady state, we're keeping all the time. I mean, in the scope of this class, it's all the same frequency. Yeah? So that's a good part of the phasor because we assume the same frequency so we can do all the math using phasor instead of the time domain. It's getting super complicated. Let me show you one example. A cosine omega t plus 60 degrees plus B sine omega t plus 90 degrees. Add it for me. You want to cry, right? Takes a while. Same frequency, so don't worry about it. Convert to phasor. So phasor, this is what? A angle 60 degrees. Oh, one thing I didn't mention. A, E, J, theta is a sine wave, right? And there's another form, it's called, what's the name of the form? Anyway, so it's amplitude, angle, theta. Same thing. Okay, same stuff. All right. So why it's a cosine, oh, I'm not asking why, I'm just telling you. So cosine omega t, cosine with a time domain, so cosine omega t is a reference. So cosine signal is a reference. We always use a cosine, because it's a sine wave, doesn't matter. It can be sine t, it can be cosine t, right? But we just need a reference. So we use cosine as a reference, because phasor doesn't carry information of time. So we just find out the reference. So let's use cosine as a reference. So whenever I'm writing down this, give me the time domain signal. What's the time domain signal? It's a cosine omega t plus theta. Wait, is that? Yeah, I think that's right. All right, so it's a cosine omega t. What is omega? It's another thing I have to cover today. So if I draw a circle, I draw a circle. That's a radian, right? It's called radian. And so what's the parameter of it? Parameter of a circle? 2 pi r. Okay. So for the whole circle, how many lengths of r's in there? How many? Yeah, it's a really interesting question to ask you, right? Ask yourself. We haven't thought about it through high school and college. I haven't thought about that as well, but now I know where does this come from. So 2 pi r for the whole circle as a length in terms of length, right? So which means for the whole length, there are 2 pi times r. So there are 2 pi r's. If you grab r here, you put in here, there are 2 pi of them. Make sense? So 2 pi of r's. Okay? So if you divide it by 2 pi r divided by what? Let me see. 2 pi r divided by r. What is this? Yeah, 2 pi, right? So there are 2 pi of r's. And so what is 2 pi over t though? What is 2 pi over t? It's how many radians per second? Let me see if that's correct. You have 2 pi radians, okay? And you have, so to run through the 2 pi radians, it takes t.
It's a period, right?
No, t is a period, yes. T is a period.
So that's frequency.
So what is this called? It's a radians per what? Second. Is that correct? Because you have 2 pi radians to run through the circle. How many radians? 2 pi radians. It takes how much time? T. So 2 pi over t will be how many radians per second? That's omega. Okay? So omega also equals, because this equals this, right? So this is because 1 over t is f, is frequency. I agree with that. You agree with that? So 1 over t, 1 over time is frequency. So eventually omega is also equals 2 pi f. So a cosine omega t plus theta also equals a cosine 2 pi ft plus theta, right? So this angle has to be what? So see here, 2 pi f t. What is this? Oh, 2 pi over t is what? Radians per second, right? T is in second. Yeah, so that's the angle here, right? That's the angle. That's the phase shift. So they are both angles, but this angle is in terms of what? Radians. Which means something pi instead of a degree. So if you see this angle being written in the degree form, you need to know that they cannot be physically added to each other. You have to convert these to radians first. Revisit this. I know it's confusing at the very beginning, but definitely revisit here. Okay. So let me give you some examples. Homework 1, first problem. VT is homework 9, the first problem. 110 cosine 120 pi t minus 60 degrees. And you know that 60 degrees is not a legit number here, right? I have to convert it to radians. Okay? Because this is a radians, there's no way that I can add it or subtract from the degrees, right? So what is the radian here? 60 degrees. It's in 360 degrees for the whole circle. And the whole circle is 2 pi in total. Why? Why is 2 pi for the whole circle? And now I'm trying to get a radians, right? Radians, yeah. So why put the 2 pi here? Total number of radians. This is the total number of angles. So for the whole circle, there are 360 degrees and the 2 pi radians. Okay, that's why I can find out how many radians I have for this degree. That's how I convert it. Super important equation. Okay. So the first question is, what is Vm? Vm is called magnitude. It's also amplitude. Magnitude. It's just the sound wave's peak voltage. What is Vm? 110. Okay? So what is F? What is F? Remember this one is omega t, right? Omega is what? Omega is 2 pi f, which is derived on the other page. 2 pi f. So in here, omega will be 120 pi. Can I find f? Yes. Cancelled. So f is 60 what? Hertz. What is omega? 2 pi f. Is that correct?
Yep.
And convert to radians. Just calculate it. Pi is 3.14. What is theta? Theta here. Minus 60 degrees in radians. Minus 60 degrees over 360. It's called calculated, right? So if I ask you in degree, this is a degree. So what's the name of the omega here? What's the name of it? Because we know the unit is radians per second. It's called angular what? Velocity. Or angular frequency sometimes as well. Angular velocity, angular frequency. How many radians per second? What is the t? What's t here? T is 1 over f. F is given. F is already calculated, so you can find out t easily. So what is the first time what's the first time after T0 that V equals 110 volts?
After 2 seconds.
So the equation, so it's a cosine something, right? Cosine what equals 1. So it's not affecting your 110 volts. It's 110 volts cosine blah blah blah, right? You want this guy to be 1 in order to having 110 volts. So this needs to be what? Look at cosine.
0 or 2 pi.
Yeah. So let's use 0, okay? Let's use 0. Did I use 0 here?
It doesn't want you to use 0.
So if you got a 0, cosine theta is this divided by this is 1. So you just want to make this guy to be 0. 120 pi t minus 60 degrees, which is convert 60 degrees to its radians. Equals what? Pi over 3? Okay? So you can find out T. Yeah, that's what I did. Okay? Any questions on this? Any question on this? It's confusing, but you need some practice. So definitely do the homework as soon as possible. It's still Wednesday, but try to do it. Try to work on it earlier, because exam on Tuesday next week, right? Start working on it earlier. Give the time to fix any errors. So now here it comes combination stuff, combination problems. So it's given that how to combine these two cosine signals. We probably don't have time to run the in-class exercise, but I'll give the problem on Wednesday, or just post it to Canvas to let you work on it. So 100 cosine 300 t plus 45
Is this a voltage or current?
voltage. It doesn't say anything. Doesn't matter, right? Just math. Okay. How to do it? Definitely not time domain, right? Like I said, since we learned Phasor, use Phasor. How to use Phasor to do the job? Convert it to what first?
Radians now.
Let's try both. See how that works. Okay. Definitely, we know the first one is what 100. 100 and since no time, it's the same frequency. You'll see, so we don't have to worry about it in the Phasor. So it's basically just 145 degrees plus 500 and what? Minus 60 degrees, right? But how can I combine them? You can't. You still can't. How to do the angles? There's no way that I can add the angles. Right? It's not like 45 plus 60. No, it's not working that way. So I have to convert it to what? The rectangular form. So it has the real number, imaginary number, so you can add them together. The real part, imaginary part, eventually convert it back. Make sense? Okay, let's do it. So what is this? 100 times what? Cosine 45. So keep in mind, the cosine here is different from the cosine here. This is cosine, the time domain cosine. This is the rectangular form, the Phasor cosine. Minus 60 and 60 are the same, right? So I can directly ignore it. Okay? Just use calculators. This can be calculated. can be calculated. Okay, these are all of them can be calculated. And eventually you got a result. I'll just directly show you. Do I have this calculator already? No, I haven't. Anyway, so let's assume it. Assume something, okay? Assume something. What's that?
Are we subtracting the last component?
Yeah, because this is minus sign here. Right? This equals this. This equals this. And expand it. You're getting this, right? Cosine negative 60 is the same as cosine 60, so I directly write it down. Ignore the negative sign over here. So you can calculate it. Eventually, you are getting A plus JB. Okay.
327 minus 362i.
How do you recover this? Convert it to like something, cosine something. How? Because it's asking to combine these two time domain signals. Eventually, you are getting a time domain signal. And now we combine it in the phasor domain, and we got this rectangular form. And now we just need to get here. So what is A from here? A squared plus B squared, square root, that's A. Omega t doesn't change. That's why it's called static form. Still 300t. Don't worry about that. What's the angle? Plus what? Arc, tangent, what? B over A. Done. This applies to multiple problems after this one, after this exact, the part A. For all the following ones, it's like the same stuff. Any question on this before we move forward? What if you see a sine wave here instead of a cosine wave? Y equals 100. I could just directly use the example here. Let's do this.
Do you need to be able to do these conversions by hand?
Here?
Yeah.
This has to be a calculator thing,
Yeah.
right? Here is a calculator.
Because my calculator just directly supports complex numbers in both polar and rectangular form.
Directly supports? What does that mean?
What was that?
Did you say directly supports?
Yeah, it directly supports that I can import
Oh.
both polar complex
You can
numbers.
directly do that?
Yeah.
Cool, that's cool. That's cool. Yeah. Yeah. You can do that, that's great. Okay, explore that, okay? If your calculator can do the job quicker, then just do it. I found a online calculator. That's when I work through the problem. I use an online calculator, but you can manually do it if you want. Either way. And so, what if you see a cosine and sine wave? Cosine. Use 60. Okay, what about this? 60 what? Since we use cosine as a reference, so directly just grab the angle here, okay? And sine wave is not a reference. It's has a 90 degree phase shift. So what you want to do is convert sine, because we know sine theta equals what? Cosine what? Cosine theta minus 90 degrees, right? Keep that in mind. We use this a lot. Why? Sine theta is this divided by this, right? You minus by 90 degrees. Cosine theta is the same thing, same length here. So sine theta equals cosine theta minus 90 degrees. So in here, you just convert this guy to what? Cosine 100t minus 125 minus 90 degrees. Okay? I can further convert it to this domain if you want. It's just have to look at the angle. But what you need to know is what's the cosine for this theta, for example. Cosine this angle. it's cosine this angle, right? But negative. It's actually this divided by this. Because this is negative, that's why cosine theta of this guy is a negative value. Make sense? So it's actually cosine theta like this equals what? Negative cosine what?
180 minus theta.
Yes.
Pi minus theta.
Pi minus theta as well. Okay? So this solves a lot of problems here and here. Oh, impedance. Impedance. We'll talk about that as well. Then we'll call today. 15 minutes. Really short. So if you convert the inductors and capacitors into its impedance form, you can directly use it as a resistor for Ohm's law. Okay, for sinusoidal voltages and currents. Just to let you know. So for example, you have this guy. This is 1 Henry. This is 1 farad. Like a sinusoidal signal here, the voltage. So convert to impedance. Because these are nonlinear components, have to involve frequency in there. And if I have time, I'm going to show you where this comes from. But just remember that impedance of, it's called ZL, impedance of ZL. So inductor impedance is what? J omega L. We just introduced omega, so you know what omega is, right? What is omega? 2 pi f. For ZC, impedance capacitor is what? 1 over J omega C. This is something you have to remember or put on the cheat sheet. I can derive it later, but what's that?
Negative.
You can convert it. So times J on the numerator and denominators are getting minus J over omega C.
Okay.
Just times J on the top and bottom, right? J times J, remember J is what? So J squared is what?
Negative 1.
Okay? So J on both sides times J on both top and bottom, you're getting this, right? So for impedance of capacitor, can either use here, use this one, either way. So this is minus J over what? 2 pi f C. Okay? So now it makes a lot of sense. So for capacitor, if you got a frequency, if the frequency goes up, the impedance or resistance, resistance, going down or going up. Frequency going up, the impedance going down or going, the amplitude. Going down, right? High frequency, low impedance of capacitor. That's why capacitor can pass AC signal and block DC signal. The DC signal has a frequency of 0, but AC signal can go up high frequency. So high frequency will reduce the impedance. It's actually coupling that AC signal to the other terminal. So AC comes through. For inductor, like what I said, you put an inductor in the circuit for 100 years. What's happening? Inductor becomes a wire, right? So DC signal, inductor for the DC signal is a wire. Okay? Why? Because frequency is low. 0. That's why it's a wire. So for AC signal, if the frequency goes up, impedance goes up. So this actually blocks AC signal. Whenever you get a noise in the ground line or power line, you put an inductor in there, it's going to block high frequency noise to make your DC power supply more static, more stable. And that's called, it's called a inductive choke. So what you do is, for example, here's the source, right? And you want to supply this voltage to something, your load. And you can have a couple inductors there. It's a really interesting circuit since I used it for one of the products I sold to company. And you have this inductor in the middle. Whenever you have a lot of AC noise, high frequency noise, it's able to block it. So only allow the DC part goes through it. So you are getting a very stable 5 volts power supply for the microcontroller. So it's more resistant to AC noises because it's rejecting AC, like choke. It's choking. No AC is allowed, only DC pass. Makes sense? Signal, and there are some concepts over here. You can also Google it, since I Googled it. I never used it in like 20 years. admittance. I'll take 1 minute to finish this, okay? Conductance. Susceptance. What are they? Admittance is inverse of impedance. This is the real part, which without J, real part of admittance. This is a imaginary part of the admittance. Some context. This is a problem asking to find out all these parameters. You know, just need to know what they are. And we on Wednesday still, okay? So what I'm gonna do is I will run these problems that ask you to do all these impedance calculations with a rectangular form. I'm gonna record one of the videos and upload it, okay? So you can work on it. No problem. I'll see you on Wednesday.
Did you give an email?
Not yet. I couldn't come yet, but I will look at it. What's your name? Just look at it.
Well, to save you time from looking at the email, I was just wondering where we get the parts for the PCBs. I was wondering where we get the parts for the PCBs.
Oh, the TA will hand it to you. The TA will hand it to you today.
Oh, gotcha. Okay, thank you.
What's up?
I was about 5 minutes late to class, so I wasn't able to pick up my sheet. Okay, thank you.